start without the birthday boy. So this is our afternoon session. We have two speakers. The first speaker, Professor Sharmodeep Bhattacharyya from Oregon State University. He graduated from our department in 2013 with Bethe, and he will talk about dependent structures in network data.
Thank you for the invitation to speak here. So I'm coming here after a long time, I've been away from Berkeley for more than 7 years. So it's nice to be back. So the talk means in this talk, the work I will be presenting, I have two main collaborators here. And one of my collaborators, Shishendu, is one of my long-term collaborators. So he's from City University of New York. He's a probabilist, but trying to switch to become a statistician. So, and Shoumendu is also a former student of Peter, currently in ISI Kolkata. So they are the two main collaborators, but there are other collaborators for all of the research works I will be talking about throughout this talk. So this is a brief outline. I don't know how much I will be able to cover out of this outline, but I will go step by step. And if I feel that I'm running short of time, then I will probably skip some of the parts. So, again, today we have been talking, yesterday also, today also, we have been talking about network data. So we know, many of you know what network data is. Network data, most of the time, is a situation where the data is given in form of a network, essentially meaning that you have the data is given in form of an adjacency matrix related to the network. So you have that as your data. Now the thing is here, as I mentioned, the topic of the talk is dependent structures in network data. So first of all, in network data, these entries, adjacency matrix entries, they are dependent on each other, because that's what the network is trying to capture, a dependency pattern between the nodes. Oh, I should remove this. So a dependency pattern between the nodes, that's what it is trying to capture. So that's why we first of all need a structure that captures this dependence pattern. And then, of course, trying to extend that, trying to capture more and more generalized pattern between different forms of network data. So that's the goal by which we are going into this kind of, you can say, building a statistical inference framework for network data sets. Now, all of this started for me also, like many other people that were giving the talks in this conference, like previously Harry mentioned, and also Jing mentioned today in the morning. Means for me also, when I was doing PhD here, Peter said that, okay, I'm doing some interesting work on network statistics. I will get you involved. Let me first get out this paper. Then after that, I will get you involved in that. So this was the work where Peter and Ayu, they tried to build a framework, a statistical framework for network data, essentially trying to formalize the dependence that is there in network data in the adjacency matrix entries. So their idea was this non-parametric view of network models, which since then has been given many different names. It has been given exchangeable network, graphon models, or what the Peter gave the name to be non-parametric network model, all of different, or non-parametric latent variable models. Several such names have been given. And previously also, there were latent space models, which were also very similar to this kind of models. So the essential idea is that corresponding to the nodes, you have a latent variable. The latent variables are usually unknown. And based on whatever the values of the latent variable are, you have a probability of edge formation between two different nodes. That's the simplest idea. So what you are doing is that you are forming a conditional independent structure here between the nodes, by which you are capturing the dependence between the edges, between dependence between the adjacency matrix edges. So essentially what you are ultimately getting is a conditional independent structure. Now, using this conditional independent structure thereafter, in the next 12 or 13 years, an explosion of papers have occurred. There has been an explosion of works that has gone on using this exchangeable structures or this kind of latent space structures. Now, so one type of extension that we can look for here is that, can we extend this conditional independence framework? That means even accounting for that means, can we go beyond this conditional independence setup? So that can be one type of extension that we can look for here to account for the dependence that is there between the adjacency matrices. But this is a model for single networks, just one network that is available to you as a data. But in the last decade or so, or even more, there has been an explosion in network data sets also. So network data has been coming in not only as a single network, but as sequences of networks or a collection of networks. So networks were not really, many of the times, just one network data that was observed, or based on which this kind of models were developed. But network data became sequences or collections, this kind of situations. Like we could get neuroscience data where there was a sequence of brain networks that were being observed in different animals. Or we could get citation networks which was changing over time. So this kind of situations occurred. And this is one of them, I like this network really because it has a nice changing pattern in the network. This is the voting patterns in US Congress where an age is drawn if two congressmen vote similarly on a single bill and no age if they vote differently. So as you can see, from 1950s onwards to something like 2011, the graph changed quite a bit. So there were, means these are Republican Democrats, there were quite a bit of number of ages between the two different groups in 1950s, whereas in 2011, there is almost no ages between the two groups. So that means this is a sequence of networks. And we can try to analyze whether there is a change point in these sequences of networks. So that can be another set of problems. Yes?
So the time goes this way, like director's guy?
The time goes like this.
Oh, I don't know.
Yes. So this is also a very nice data set which captures this kind of behavior. So that means that the network data sets, they also have been evolving. So not only that we want to capture more involved dependence within a single network, but we also want to capture dependence in the sequences of networks. So that's why people have tried to form this kind of more complex network structures, not only single networks, but this kind of multi-layer networks, where essentially you have a number of single networks being combined into one large structure. So previously, Jing was mentioning also about this kind of multi-layer network. So most general form of multi-layer networks are that you have several single networks. Each of those single networks can have different node sets. There is connection between the nodes in a single layer, as well as between the nodes of different layers. So you have, say, nodes here, say 2 different layers here. In one of the layers, you have 4 different nodes. There is connection between them. In another layer, you have 3 nodes. You have connection between them. And then also you have connections between these nodes. So in this way, that means that completely different types of, there are many examples of this kind of behavior. Like say, in financial network data, this might be different financial, this can be different financial institutions, this can be different financial measurements, and they might be connected in between them as well as between themselves. So this kind of things can occur. Similarly, we can think of this as a temporal network also. That means networks evolving over time. So in the very general format, therefore, is that there are several networks and then there are connections between them, thus forming a multi-layer network. And more special cases of them are things like what are known as multiplex network, where essentially the nodes that are there, they remain the same. However, the age structure between each of these layers, they change. So that is usually called, what is sometimes called as multiplex networks, but sometimes they are also called multi-layer networks because there is some interchange in terminology many times. They can be also, in temporal networks can also be special cases of this, where one network is, that means age structure of a network is evolving over time, and that is captured in a temporal network. So any kind of sequences of networks can also be considered as a multi-layer network or a generalization of a single network structure. So that's why our goal then becomes twofold. means at least that's how we are tackling the problem of dependency network models. First of all, there can be dependent in a situation where you have a multi-layer network, you can have dependence across layers in the network sequences. So we are considering here a situation. So of course, we are considering the simpler networks, multiplex and temporal network. We will not be going for these very general multi-layer networks, but we will be considering only multiplex and temporal networks where the node set remain the same, but the edge set can change, that kind of a situation. So in that kind of a situation, there can be dependence across the network layers. That means adjacency, entry of an adjacency matrix in one layer can be dependent on the entry of the adjacency matrix in another layer. So there can be dependence across multiple layers. And this dependence we are trying to model in two different ways. One is direct dependence of the adjacency matrices. The second part is that the adjacency matrix is being generated from some kind of a latent model. And the parameters of those model, they are the ones which are related. That means they follow a stochastic process. And then the parameters are coming from the stochastic block. And the adjacency matrices are being generated conditionally independently. So there is still a conditional independent structure in the second form. And in this form, there is no conditional independent structure in that way because the adjacency matrices are related to each other across time or across layers. So this is two types of generalization that we will be considering while considering dependence across layers. And then we will try to also go for dependence in edge formation. That means breaking the conditional independent structure. So we'll try to break the conditional independent structure using some ways and then try to form, even in a single network, try to have an edge structure which is not conditionally independent. And then trying to see how we can do, whether we can do anything with those kind of structures. So that's how we will try to bring in more dependence into network data structures. Of course, as you can see, there are very many facets to this problem and then many facets to this, the way we are trying to tackle this problem. I will try to touch some of the aspects, not much, and there is a lot of works to do also. Means we are only starting on different aspects. So some of these works we have submitted for publication. Some of these works are ongoing. Some of the works I will mention as future directions. So all sorts are there. Okay. So the main questions that we will be focusing on all of these are these three main questions. One is community detection. That means in situations like this, we will try to find whether there are communities in these networks. Another will be change point detection, specifically if you have sequences of networks, whether we can find structural breakpoints in the network sequences. And another type of problems will be essentially the typical statistical problem, parameter estimation, or in this kind of situations, there will be several population parameters of the network models can be formed, whether we can estimate those. So those will be the three main categories of problem we can say, because all of these problems can have various different sub-problems in them. So these are the three different categories of problem that we will be interested in. Now, let us go first to the situation of dependent layers. That means network sequences with dependent layers. So we will be considering a situation where you have a multi-layer network, but the networks can be dependent. So first thing, so as I said, we will be forming two different types of dependencies. One is direct dependence of adjacency matrices. Another is the dependence of the model parameters. Okay, so let me first tackle the problem of dependence of adjacency matrices. So forming this dependence in itself is a difficult thing. So for this, we had two additional collaborators or students, you can say. So these were master students from Indian Statistical Institute, Kolkata. So by now they have all joined as PhD student in, one is in UPenn, another is in Columbia, I think currently. But they helped us quite a bit doing simulations and things like that in this project. So, okay, so the dependent layer formation, the formulation that we will be considering here is this very simple one, because we wanted to start with something simple, because currently there is not much work in this domain where there is this kind of dependency in network structures. So the formulation that we consider, you can consider this as some kind of a lazy stochastic process that essentially means that in each of the adjacency matrices will be equal to the adjacency matrix of the previous time point with some probability. And with some probability, you will be generating a new adjacency matrix independently. So the dependence here comes because you might be repeating the same adjacency matrix. So that's how the dependence is coming here. And the probability alpha here, the probability with which you are keeping the same, the adjacency matrix from the previous time point is alpha. And the probability with which you are generating a new adjacency matrix independently, that is 1 minus alpha. Now, in the situation of completely independent situation, in that case, this alpha will be equals to 0. That means you are independently generating another adjacency matrix. And this is the format that is mostly used nowadays. So like the talk that Jing was giving, he had independent adjacency matrices in different layers. So most of the talks, that means the works that has been done works under this format where you have this alpha equals to 0. Now, of course, when alpha increases, then essentially what you are having is that all the adjacency metrics are remaining the same. So although you have, say, t different layers, but essentially you have just one adjacency matrix. So if alpha equals to 1. So now we are expanding that situations that it is somewhere in between. So there can be an dependent situation. This is the simplest form of dependence we could think about. But even analyzing this simplest form of dependence was also not so easy, because most of the conventional methods didn't work. So
I mean, you could have done something where each edge gets flipped independently with probability alpha in each step.
yes, that can be also another way to deal with each edge gets flipped.
Yes, here either you forget the whole network or you keep.
Yeah, here either I forget the whole thing or I keep. But if we flip, I remember some part of it, some part I forget. Yeah. So it's a bit different kind of thing, but yeah, but I cannot say about the flipping one, but that how hard the analysis will be. But this one also means, yeah, we have to give some effort to do the analysis. Yeah, but yeah, those kind of simple mechanisms can be there to go from the independent setup to the dependent setup. So for this one, what we first try to do is this kind of step we first wanted to see, that if you do then aggregated adjacency matrix or aggregated Laplacian matrix based on these layers, do they concentrate? Do they concentrate to their mean? So that's the first thing we wanted to try, because this kind of results, concentration to their mean, concentration to their expectation, these kind of results are used for community detection, change point detection, all of different things. This kind of concentration is used. And we try to see the concentration in the spectral now. So what we essentially show that, okay, this kind of dependent format, if you form the aggregated adjacency matrix or the aggregated Laplacian matrix, in that case, they are near to they are concentrated around their expectation or the mean version. And that expectation is controlled, first of all, by T, and T here is the number of adjacency matrix you have. D max and D mean are the minimum of the degrees of all the adjacency matrices. And this C1 alpha is the one that contains alpha. And this C1 alpha and C2 alpha are actually both of the order of 1 by square root of 1 minus alpha. So as you can see in this kind of in this setup, that as alpha approaches 0, in that case, this rate becomes like square root of TD max. However, this 1 by square root of 1 minus alpha starts becoming larger and larger as alpha starts going near 1. So as you can see, it's very intuitive. Here also we can see that as alpha starts going near 1, that means we have just one adjacency matrix, data is reducing. So our concentration becomes more and more difficult. And when alpha is trying to go to 0, we have better concentration because we have many data, many independent copies of the data. So our concentration becomes better. So that's what we are capturing here. And the rate we are coming up with is of the order of 1 by square root of 1 minus alpha. So that's the rate we get. And for both Laplacian and adjacency, the difference is that because one is Laplacian and another is adjacency, one is controlled by D max and other is controlled by 1 by D mean. So that's the effect of the Laplacian and adjacency. So now we have a result for this kind of situation. Now, as I said, means here C1 alpha and C2 alpha are of both of the order of 1 by square root of 1 minus alpha. So when alpha equals to 0, the concentration is the highest, the best kind of concentration we are getting, because we are adding up all of the adjacency matrices. Whereas for alpha going to 1, the concentration becoming worse and worse, ultimately you have no concentration because you have just one data point. Now, none of the known techniques, that means matrix Bernstein types, combinatorial arguments, path counting arguments, none of those works for it. Here, we had to use a sort of a geometric random variable kind of argument here to prove this kind of concentration result and a large deviation result on that. And so by this, actually, we can capture this whole range from very weakly correlated network layers to strongly correlated networks layers, all we can here account for by using this concentration inequality. So now, of course, as we can see here, this is in the simulation results, we can see that the errors that are there in this is the spectral norm errors. As alpha increases, they also increase in both adjacency and Laplacian matrices. These are two, in the bottom, you have two different graphon networks generation from continuous graphons, and on the top you have networks generated from stochastic block models. For both of the kind of situations, you have this kind of concentration behavior. Now, then we can use this kind of concentration results to do both change point detection and community detection, where you have dependent networks. So for change point detection, we considered a simple situation where you have one single change point. So at certain time point, you have the expectation of the adjacency matrix is Q1 and it changes to Q2 at certain time point, and you want to capture that. And you can try to do that. Means the main signal here is the spectral norm of Q1 and Q2 here. So all the results will be in terms of that spectral norm. And you can just use a single point change point detection method where you find the Q-sum statistic on one part of the sequence and Q-sum statistics on the other part of the sequence, and then just take the difference. And where the difference is maximized is the change point. So that's the simple single change point detection method. And the statistic that we are using in order to find the differences in Q-sum is this kind of a statistic where we are scaling this Q-sum statistic using this scaling factor. The scaling factor is controlled by this xi parameter, which usually people take as half many of the times, but it can be changed in different situations. So our general result, we just kept in the xi parameter here. So in our general parameter result, we could see that, of course, this how good the estimate of the change point is depend on the signal, but it also depends on this square root of 1 minus alpha parameter. So not only that, it's usually the main results that we get without the adjacency, this kind of dependence, is that this 1 minus alpha parameter is not there. Now this extra 1 by square root of 1 minus alpha parameter is there while we are finding the rates. And that's capturing the dependence across the network layers. Actually, so this log n term that comes here, this log n term is an extra term. We don't think that it should be there in this rate, but this was the best we could do in our analysis for now. But I think a better analysis probably will get rid of this log n term. And another thing I should mention is that it's still in this concentration result. It's still under this degree assumptions that TD max have to be greater than log n or polylog n. So this is, we also think that this can be relaxed if we can properly do the analysis or some other ways. But this is, for now, this is what we can get. And similarly for this is the Q-sum procedure, and similarly, we can do community detection also, where we have a sequence of network layers, but we have the same community structure, but the adjacency matrices are dependent on each other. That kind of things can go on. So in that kind of a situation, we can also estimate the unknown community membership matrix using spectral clustering, either using the spectral clustering on adjacency or Laplacian. Both will give you, you can bound the misclustering errors here. And in both situations, the factor of 1 by square root of 1 minus alpha will be the extraneous one that will come in the rate. So that's the first portion, that you have dependency network layers, but the dependence is coming from the dependence in adjacency matrices. The second one we go, so this is also the simulation for result for SBM, that means for community detection, the same thing. We can see that as alpha increases, you have worse and worse errors for different situations. So next, we go for the situation where there can be dependence in network layer model parameters. So that means that here, the situation is that you have T different graphs, there are adjacency matrices corresponding to them. But these adjacency matrices are being generated. That means say they have a mean, which we are calling that as PT, but this PT follows a stochastic process. So the network model parameters are the ones that are dependent on each other. They are the ones that are following a dependence pattern. So this is a bit different because here the adjacency matrix, they are still conditionally independent. Once you know PT, all the adjacency matrices are conditionally independent of each other. But this PT can be dependent on each other. So the dependence is coming from the model parameters. Okay. So, then we can try to see that, okay, in this kind of a setup, if we have this kind of a sequences of network model parameters, and also we have the adjacency matrix, which is being generated from that. But we are assuming here that the community membership matrix is something that is remaining constant, not changing. And we are trying to find that community membership matrix. So just like Jing was mentioning in the previous talk, you can use the squared adjacency matrix here in this kind of a situation. So we also took the similar one, but we did this long back. We took the similar kind of squared adjacency matrix, but we took out the diagonal. So the method means the community detection algorithm was that we took the sum of the squared adjacency matrices, and then in the squared adjacency matrices, first of all, we had to take out the diagonal. We took out the diagonal. And then not only that, we tried to get rid of the large degree nodes. So in the adjacency matrix, because that's the one that creates problem in concentration of the adjacency matrices towards their mean. So what we did was that we took out the high degree nodes, and we had two different thresholds based on both the maximum degrees and also the mean degrees. We had two different thresholds. Based on that, we took out the high degree nodes. And once we took out the high degree nodes, we had this adjacency matrices, which was thresholded. That means high degree nodes are gone. And also the diagonal is not there. In this kind of a situation, if we try to do a spectral clustering on this new thresholded matrix, and we can try to use the results of the spectral clustering to find an estimate of the unknown community membership. So here we are doing two different operations. We are taking out the diagonal as well as we are thresholding the high degree nodes, thresholding them out. So once you do that, what we see, the kind of result that we see is that in this kind of a situation, first of all, of course, you need a condition on the smallest eigenvalue of the sum of B square matrices, because that's the eigengap that contains the main information about whether the clusterable structure is there or not. And then along with that, we see an interesting structure here is that a nice interplay between the number of layers and the degree of each of the networks. So what we see is that if the degree of the networks, the maximum degree, if that is greater than 1, in that case, independent of whether n is large or small, you still have this kind of a concentration with a rate of TD to the power of -1, depending on n. So in the situations where you have n small, it is determined by TD. And when n is large, also TD controls this rate. Now, in the situation of d less than equals to 1, this rate differs in that it is dependent on TD square instead of TD. So this rate on which the number of layers are related, that changes from whether it is related as in proportional to 1 over t or in proportional to 1 over square root of t, depending on the situation, depending on whether you have what's the interplay between the number of nodes in the network and the number of layers in the network.
Oh, John, we have only 5 minutes.
Okay.
30 slides.
All right. So that's the situation, but this is for independent layers. Now, if the layers were dependent, if the layers were not independent, in that kind of a situation, of course, we have to consider a stochastic process. Now, instead of considering a stochastic process on the B matrix, what we consider here, the most important thing actually is the smallest eigenvalue of B. So instead of that, we consider the stochastic process on the smallest eigenvalue of B. So if means, and also on the maximum degree variable, which is also a random variable. So we considered a stochastic process on these two. And what we considered were, we considered a mixing condition on this smallest eigenvalue, the smallest eigenvalue process of the B stochastic process. So this mixing condition is needed to control the rate of the adjacency of this concentration of the adjacency matrices. So we considered a mixing condition, alpha mixing condition on this smaller, whether this smallest eigenvalue takes a value of 0 or not, based on that stochastic process. And then also we try to see, so in the assumptions, ultimately we try to control for a function of this T and D, such that this T and D function is there to control for this kind of a situation. That means what is the probability that smallest eigenvalue takes a value of 0. So we want that probability to go smaller and smaller as TD grows to infinity. We don't want this to happen, because if this happens, there will be no community finding. There will be no community structure. So we want this probability to be lower and lower as TD increases. And we want to capture that using this phi function. And also we want that this expectation of this phi is controlled. Expectation of this lambda, the smallest eigenvalue process is controlled. Under this kind of a condition, this assumptions conditions, we can again show that the amount of mistakes we are making in this squared adjacency matrix based community detection, spectral clustering, we can control the amount of the amount of errors that we are making. And of course, that depends on the stochastic process, mainly the smallest eigenvalue of the stochastic process and the degree parameters. So this TDN and TDN square, these parameters, as well as the smallest, the lambda KT, the parameters of that smallest eigenvalue process. Based on that, we can show that it converges. That means you have a consistency in the network community membership identification. So I will skip this change point for problem formulation for this kind of dependent model parameter setup. Instead of that, let me just go into this detour also I will skip in the interest of time. So in this detour, I considered a situation where even for sparse matrix, you can determine the number of communities consistently using a variation of the Bethe Hessian matrices, which previously Kahn and Lisa used. So I will skip that portion also. The one thing that I wanted to mention, another form of dependence, as I was saying, is networks with dependent age structure. Now, in this kind of a setup, as I was saying, that networks, we usually want networks to have this kind of nice desirable properties. That means sparsity, small world property, power law degree distribution, transitivity, and presence of a low rank structure or community structure. So this kind of 5 different desirable properties we usually want. But many of the times, the models that we consider, like say the exchangeable network model that we consider, that usually cannot have these 5 properties simultaneously. It's if you try to take 4, 1 will be missing many of the times. So that's why in this kind of a setup, specifically say if you try to get a sparse, transitive, and low rank matrices from graphon models, you cannot really get that because of the exchangeability property. So that's why what we considered was a very simple extension, was this what we called as transitive inhomogeneous Erdos-Renyi graph, or a transitive expansion of the exchangeable random graph models, where at the first step, we will get from an exchangeable model, we will get a network, inhomogeneous Erdos-Renyi networks, or an exchangeable model network. we are here considering very simple situation that we have a P matrix which is generating the network at the 0th step, and we have a triangle closure parameter of delta n, which is just one parameter. This is the simplest case. This can be expanded, of course, and we are repeating this process k number of times. That means that's what we are calling as a tire k model. That means we have starting from step 0, and at each of the steps, what we are doing is we are doing a triangle closure. We are taking two different nodes. We are seeing whether these two different nodes have any common neighbors or not. If they have even one common neighbor, we will form an edge between these two nodes with probability delta. So that's the triangle closure operation. And after we have an inhomogeneous Erdos-Renyi graph or exchangeable network model graph, we will first try to close all the triangles that we can. That will give us a tier 1 model. Then we will take that network and then again try to do triangle closure. That will give us the tier 2 model, and so on and on. So we will repeat this k number of times in a tier k model, but in a tier 1 model, we will do this just once. So, and the idea is that within using this triangle closure, you can get all 5 properties that you want from an extending from the exchangeable network model. So just to show you some simulated results at least. So here we can see that in this kind of situation, this is generated from SBM. The network is sparse in this kind of a situation. And in the case when we are doing tier 1, 2, 3 also, that network is still remaining sparse. The average degree is still like varying between 1 to 2. But the number of triangles, they are increasing hugely. So this is for SBM model, the number of triangles is almost close to 0. Of course, we are normalizing it, but it is increasing step by step when we are going from tier 1 to 3. Similarly, when we are considering geodesics, the graphs are becoming smaller and smaller world properties are coming. And also the eigengaps are increasing. That means you are having a more nicer low rank structure. So all of these are going on when you are introducing the tier structure in the exchangeable networks. And later on, we try to use that for different kinds of problems. Subgraph count distribution, community detection, change point detection. Many of the works are ongoing. Some of the works are close to finish, and some of the works we are submitting. So yeah, so a huge number of works here. I will not go into the example of change point detection anymore. We don't have time for that. And there are many future directions here, as we can see. There are extension of the tier k models, extending the dependent setup of the dependency adjacency matrices. I used a very simple setup. Variation of these community levels over time, which I didn't consider. My community levels were remaining constant throughout the time, and also how to incorporate covariance. So all of these are good future directions. Last, an advertisement that we have openings. If you have students or you are a student, you are encouraged. And yeah, some of the references. Thank you for listening.
Take one question. Oh.
Yeah, let's hope that you do.
Yeah. Thank you, Sharma. That was a fun talk. So for the third talk today, I see this interesting theme that Peter hinted at in his question earlier today. So we saw that local information in the sense of neighbors or neighbors of neighbors, something like that is helpful. Then we saw in Jing's talk that squaring the adjacency matrix seems to help. We see that again here. Something is going on here where looking at like squaring the adjacency matrix is really just looking at 2-hop information instead of 1.
You can see that actually in the result also. Here in the result.
I missed that. Can you speak to that a little bit?
So here actually you can see that. So it is depending on both TD square and TD. TD is just the connection. That means what is the probability of an edge formation? Because it's taking into account the number of times and the degree. Whereas TD square is that hop. That means number of common neighbors. So if TD square is dominating, means depending on how the adjacency matrix is being formed. If TD square is dominating, then that is the one that is dominating the rate. That means number of common neighbors you have. But if TD is dominating, in that case, TD is dominating the result in that case. So there is an interaction goes on here between the number of common neighbors you have and the number of edges you have between two different vertices. So yeah, the number of common neighbors plays a huge role here. And that's why you have this separation in the rates, the amount of errors that you are making. So yeah.
Okay, let's take the speaker again.
Okay.
Our second speaker is Ben Brown. He's now working in Lawrence Berkeley National Lab. He got his PhD from Berkeley